to talk about infinite limits now. Infinite limits. Infinite limits. Infinite limits means that limit is infinity. It's infinite. For example, here are the x and y axis. You have a graph that goes like this and like that. And we call this number 7. Now what's happening is the graph is getting closer and closer to this line. Never touch it, never cross it. Gets close to it. So the limit, and let's give this graph a name, let's call it g of x. The limit as x goes to 7 from the left of g of x. If you're a little bit less than 7, it's going up to positive infinity. If it's a little bit more than 7, it's also going up to infinity. I meant to write it this way, excuse me. Now, I'm not suggesting that they're always going to be both plus infinity. Sometimes one will be positive and one will be negative. What do I mean by one? Are the left limit or the right limit? For example, this graph, so use 7 again. As you get closer and closer to 7, so as you get closer and closer to 7, from the left, the graph is going to negative infinity. Getting closer to negative infinity. But from the other side, it's getting closer to positive infinity. And let's call this j of x. So the limit as x goes to 7 from the left of j of x, this is going to be negative infinity. Because a little bit to the left of 7, the graph is going to negative infinity. The limit as x goes to 7 from the right, a little bit more than 7, is going to positive infinity. Okay. So, given a graph, I think it's pretty straightforward to tell us the limit as x goes to a particular value, if it's going to positive infinity or negative infinity, or it's not going to infinity. Now, I think you notice that I kept drawing this vertical line, and I'm saying the graph is getting closer and closer to it. The graph starts getting closer and closer to that line. This line has a special name. It's called a vertical asymptote. And basically, so here's the x-axis and here's the y-axis. Basically, you have a vertical asymptote when an x value makes the denominator equal to 0, but this x value does not make the numerator 0. Does not make the top equal to 0. Because if the top is not 0, it's 7. And the bottom equals 0. That is, the bottom is getting closer and closer to 0. Like 1 over 100,000. This is a small number, 1 over 100,000. For 7 divided by it, if you do the math correctly, you get a very large number. As the bottom goes to 0, the fraction goes to infinity. Now, if either the numerator or the denominator was negative, then the fraction will be negative 700,000. A very large negative number. So you have a vertical asymptote for every time you have an x value that makes the denominator 0 and not the numerator. And you're going to have infinite limits at these vertical asymptotes. So one strategy or one exercise should naturally be find the vertical asymptotes. Find the vertical asymptotes for the following functions. It is find the x values and make the bottom 0 and not the top. And suppose you have the first function is 1 over x squared. Okay, so you're going to have a vertical asymptote when the bottom is 0. Now the top is never 0. The top is always 1. It's never 0. You have a vertical asymptote when x squared equals 0. Well, what squared gives you 0? Only one number, 0. You have a vertical asymptote when x is 0. How about you have f of x is equal to x squared over x squared plus 5x plus 6. Okay, you have a vertical asymptote when possibly when x squared plus 5x plus 6 equals 0. Well, if you factor this, you get x plus 3 times x plus 2 is 0. Well, if this times that is 0, then either the first factor is 0, that happens when x is negative 3, and the second factor, is 0 when x is negative 2. Now, if you square, the numerator says to square x. If you square either of those numbers, you don't get 0. That is, these numbers, negative 3 and negative 2, they make the bottom 0 but not the top. So you have vertical asymptotes when, final answer, when x is negative 3 and when x is negative 2. That is, I assure you that if you were going to graph this, here's the y-axis. If you were going to graph this, and here's 2 and here's 3. I'm not going to try to graph this right. I'm not even going to try to graph it wrong. I'm not going to think about how it should look. But I guarantee you, near those dashed lines, it's going to be going to infinity. Maybe it'll go up to infinity here, do funky things in the middle, and then go down to negative infinity. Maybe here, it'll get close to the x-axis. But I guarantee you, it's going to go to infinity at that vertical line. Maybe it goes down to negative infinity, but it's going to get close to that line. Okay, it's always going to get close, go to infinity at the vertical asymptotes. Whether they're positive infinity and negative infinity, we're going to talk about how we tell. This graph, for example, could have gone like this. It's going to get closer to the vertical asymptotes at either high or low. Extremely high or extremely low. High means is going up. Low means is going down. It's not going to get close like that. It's not. It's either going to go up to positive infinity or it's going to go down to negative infinity. That's what's going to happen at vertical asymptotes. Each and every time you have a vertical asymptote, that is what's going to happen. You cannot think of a case when it wouldn't. Now, I guess at this point we should talk about removable discontinuity. Removable discontinuity. Okay, suppose you have a function that's undefined because it makes the bottom 0. But it also makes the top 0. Suppose you have f of x is equal to x squared plus 5x plus x on top, and you have x plus 3 in the bottom. Well, what is f of negative 3? Well, the numerator is going to be negative 3 squared plus 5 times negative 3 plus 6. Instead of x, I just write negative 3 in brackets. In the bottom, you're going to have negative 3 plus 3. And if you work it out, you get 0 over 0. For example, negative 3 squared is 9. Add 6, get 15. But now add negative 15. 15 plus negative 15 is 0. And the bottom is 0. But this is not anything. This is indeterminate. We need to investigate further. Now, if negative 3, using pre-calc now, if negative 3 makes the numerator 0, then x minus negative 3, or x plus 3, must be one of the factors. And the two factors have to multiply out to 6. So the other factor is going to be x plus 2. And the bottom is x plus 3. Well, this cancels out. And what you get is x plus 2. But this is provided, see, x plus 3 over x plus 3 is not equal to 1. I don't care what your teachers have told you, it doesn't equal 1. They're being sloppy when they say that. X plus 3 over x plus 3. If the numerator and the denominator are equal to one another, like I agree, 7 over 7 is equal to negative 2 over negative 2, which is equal to 0.8 over 0.8, and those all equal 1. But so the top and the bottom are equal, we seem to get 1, but not always. 0 over 0 is not 1. Okay, it is not 1. A fraction is 1 if the top and the bottom are the same, but they're not equal to 0. So this fraction is equal to 1, provided the top is not 0. When is x plus 3 not equal to 0? When x is not 3. It is indetermined if x is 3. I meant to say negative 3. Okay? X plus 3 over x plus 3 is 1, provided that the top and the bottom are not 0. That is, provided x is not negative 3. Okay. So, let's go back to the top for a moment. I crossed this out as if it were 1, and I said 1 times x plus 2 is x plus 2. But this is not always 1. It's not 1, or it's a 1, provided x is not negative 3. Okay, so what we have is, and now you have to start getting a strong command of what equal means. A lot of students would suffer greatly or unnecessarily with the problem I'm going to ask in a moment. Let me just erase this, please. I'd like to know what this equals when x is 10. What is this equal when x is 10? Okay. Now a lot of you would say, oh, this is simple. 10 squared plus 5 times 10 plus 6 over 10 plus 3. Me personally, I could have done 10 of these problems by now. And it's not because I'm better than you. I know that as long as x is not negative 3, this equals x plus 2. 10 plus 2 is 12. Okay? This and this are equal. They're the same, except when x is negative 3. And to convince you, this is 100, this is 50, that's 6, plus 6 over 13. Well, 100 plus 50 is 150 divided by 13. Well, I claim that's 12. Oh, 12 times 13 is 146. Well, I know that's not true. 36 is 156, which is correct. 13 times 12 is 156. That is, 13 goes into 156 12 times. Goes into 13 goes into 15 one time with 2 left over. And 13 into 26 goes 12 times. This really equals this. So now, if somebody asks you, what does this equal when x is 4.5, you should respond with, that's simple, 6.5. Because 4.5 plus 2 is 6.5. Okay. Now, I want to erase this, and then I want to ask you one more of those kind of questions, that is, what does this equal when x is, I won't say 10 again, I won't say 4.5, but I'm going to say negative 3. Now, on the left-hand side, when you plug in negative 3, remember, this equals the left side. When you plug in negative 3, you get 0 times negative 1 over 0. This is indeterminate. I mean, you want to plug negative 3 in here, you get negative 9, positive 9, excuse me, plus negative 15 plus 6. That's 0. Negative 3 plus 3 is 0. You get 0 over 0. So now, what did you plug in negative 3 in the right-hand side? That is the side that just said x plus 2. What about when you plug negative 3 into the right-hand side that says x plus 2? Well, negative 3 plus 2 is negative 1. They didn't agree. This did not equal x plus 2. Okay? Because at negative 3 we claim. We stay at negative 3. They're not equal. Now, if I want to draw this, if I were to draw this graph, the graph being this mess, if I were to draw this, the easiest way to draw it is to draw x plus 2. After all, almost everywhere it equals x plus 2. So, do it here. Y is equal to x plus 2. If x is 0, 0 plus 2 is 2, so y is 2. When x is 0, I go up 2. If x is 1, 1 plus 2 is 3, so y is 3. And with 1, so this is the graph, y is equal to x plus 2. Negative 1, negative 2, negative 3. Now, if I don't want x plus 2, but rather I want this graph, just have to do one thing. I have to remove -3. Because when x is -3, I don't get an intelligent answer. This is called a removable discontinuity. Why is it removable? Because if I redefine this one point, if I say everyone, when x is -3, y is -1, then it's continuous. Okay, this is called a removable discontinuity. Now, when do you have a removable discontinuity? Well, why was -3 a removable discontinuity? And the answer was, we crossed off x plus 3 over x plus 3. Okay, that is, there was an x value, namely -3, that made the numerator and the denominator equal to 0. Whenever that's the case, you have a removable discontinuity. You have a removable discontinuity when an x value makes the top and the bottom both 0. And after you cross it out, and after you cross out that removable discontinuity, it doesn't make the bottom 0 anymore. How might it make the bottom 0? Well, if you factor the top and you get, say, x plus 5 times x plus 9, and in the bottom you have x plus 5 squared, or x plus 5 times x plus 5 times 2x minus 1. Well, when x is -5, it makes the top and bottom 0. But the problem is that now it's a vertical asymptote. Either a value that makes the bottom 0 is going to be a vertical asymptote, or it's going to be a removable discontinuity. After you cross off what you think is a removable discontinuity, if that value still makes the bottom 0 and not the top 0, it's a vertical asymptote. For example, if you had x plus 5 a second time on top, well, now it cancels out, and 5 makes the top 14, 5 makes the bottom, I think, 9, everything's okay, it's removable. But if you had another x plus 5 in the bottom, that would be a vertical asymptote. Now, what if this wasn't here? What if you had another x plus 5 in the top? Well, that's fine. When x is 5, you have 14 times 5 plus 5 is 10. I think that's 140 over 2 5s minus 1 is 9. That's okay. That's okay. So if after you cross out cross out all the x plus 5, one from the top, one from the bottom, and then you look, and if it makes the bottom 0 but not the top 0, it's a vertical asymptote. If it doesn't make the top or bottom 0 anymore, it's removable. Okay, this is tricky stuff. I hope I did a decent job in explaining it. So now, I guess I'm going to give you some functions, and I'm going to ask removable discontinuity or vertical asymptote. And I'll tell you that f of x is, say, x squared minus 1 over x plus 1. Now, clearly, so we want to see when the bottom is 0. The bottom is 0, bring the 1 over, is -1, when x is -1. Now, the question is, does it make the top 0? Is -1, is x squared minus 1. Well, that's 1 minus 1. Ah, that's 0. It made the top and bottom 0. That means We don't know what the answer is here. We have to look further. The bottom is x plus 1, and when we factor the top, we get x plus 1 times x minus 1, and we cross off x minus 1 as if, over x minus 1 as if it's 1, and we get x minus 1. Okay? Now, when x is negative 1, this is just negative 2, and that's fine. So we now say we have removable discontinuity at x equal negative 1. Okay, this made the bottom 0. Okay, if after we factor and we cross out, we plug in negative 1. If we get back an intelligent answer, like negative 1 minus 1 is negative 2. It's an intelligent answer. It's removable. Okay? If you had that g of x is equal to, I don't know, x squared minus 4 over x plus 1, well, the bottom is 0 when x is negative 1. When you plug in negative 1, you get negative 1 squared minus 4 over negative 1 plus 1, which is negative 3 over 0. Okay, this value, this is a vertical asymptote because it made the bottom 0 but not the top. You have a vertical asymptote at x equal negative 1. Okay. Now, let's go back to the last one because I realized maybe I didn't do such a great job. Let's go back to the last problem. We took the denominator and we found that it was 0 and negative 1. And then we plugged in negative 1, at least I should have. Negative 1 squared is 1, minus 1 is 0. Negative 1 plus 1 is 0. Since we didn't get knocked 0 over 0, we have to investigate further. And what we discovered was when we factored out the x plus 1, we crossed them off, and then you had x minus 1. And when we plugged negative 1 in there, we got back a nice answer. That's what made it removable discontinuity. We've removed the discontinuity. We removed the bottom from being 0. For example, what if you have a problem like this? I tell you that capital F of x is x squared minus 4, and the bottom is x cubed minus 4x. Okay, where do we have vertical asymptotes or removable discontinuity? So we take the bottom and we set it equal to 0. And we factor. Each of these terms, I can pull an x out. X times x squared gives me x cubed minus x times 4 gives me 4x. So this product is 0. Okay? But I'm still not done factoring. I can't factor x, but I can factor x squared minus 4. It's the difference of squares. Over here, x is being squared. Over here, we can think of 2 as being squared. Write that down 2 times. One with a minus, one with the plus, equals 0. So either this factor is 0, and that happens when x is 0, or this factor is 0, that happens when x is 2, or this factor is 0, and that happens when x is negative 2. Okay, let's look at 0. I'm going to test x equals 0. Well, when I plug 0 in, I get 0 squared minus 4 on the top. On the bottom, I get 0 cubed minus 4 times 0, which is negative 4 over 0. If an x value makes the bottom 0, but not the top, we're done. We have a vertical asymptote at x equals 0. We're done. We know about 0. We're done with 0. Let's go to 2. We are going to test what happens when x is 2. Well, when I plug 2 in, I get 2 squared minus 4 over 2 cubed minus 4 times 2. I get 4 minus 4 over 8 minus 8. Oh, I get 0 over 0. Now we need to look at this further. We need the factor. We need the factor. X cubed minus 4x. Well, coincidentally, we did factor. We factored the bottom. We got x times x minus 2 times x plus 2. And we got the x minus 2 times x plus 2 from x squared minus 4. But that's exactly what the top is. X minus 2 over x minus 2, x plus 2. Well, the x plus 2's cancel, one from the top, one from the bottom. Same with x minus 2. So we get 1 over x. And when we plug 2 in, we get our half. As long as you get back an answer, an intelligent answer, that is the bottom's not 0, you have a removable discontinuity at x equals, we were testing 2, at x equals 2. Okay, let me erase part of this, and now we're going to test for x equals negative 2. Now in studying this, you need to study the steps. Don't worry about doing a million problems. Study the test. We are now going to test x equals negative 2. Well, negative 2 squared minus 4. I'm just plugging in negative 2. Negative 2 cubed minus 4 times negative 2. You're going to get 0 over 0. That means you need to factor. Okay? That means you need to factor. And let her see what happens after you factor. Well, you factor the numerator. I'm factoring this whole thing here. When you factor the numerator, you get this. When you factor the denominator, we already did. We got that. X plus 2's cancel. X minus 2 cancel. If you have nothing on top, put a 1. You have 1 over x. But when x is negative 2, this gives us negative a half, which is an intelligent number. We have a removable discontinuity at x equals negative 2. Okay. We're going to try one more. One more. Here's going to be a case where the top, in our last case, the x's that made both the top and bottom 0 were removable. This will not be. Suppose you had that h of x is x minus 3 over x squared minus 6x plus 9. Okay, so you want to know where you should investigate. That is, let's factor the bottom. The bottom is x minus 3 squared. Okay, since this is x squared, I'm going to try x followed by a number times x followed by a number again. And the two numbers should multiply out to 9. But they should add up to negative 6. And the two numbers that multiply out to 9 but add up to negative 6 are negative 3 and negative 3. So what makes the bottom 0? Okay, what makes the bottom 0? X is negative 3. So we need to test what's going on there. We have either a vertical asymptote at negative 3 or a removable discontinuity at negative 3. So what we do is we simplify. We simplify. We kill off one factor of x minus 3 in the top, and we kill off one of the 2 in the bottom. So now we have, something's wrong. I meant to say this is 0 and x is 3, not negative 3. So what we get is 1 over x minus 3 after we're done reducing. And here's where it comes together. When you plug in 3, in this case you get 1 over 0. If you got 1 over 4, it's removable. If you got 0 over 0, you didn't cancel enough. If you get 1 over 0, it's a vertical asymptote at x equals 3. Look at the different ones I gave you and study those steps. Find numbers and make the bottom 0. Cancel out top and bottom. If after you cancel out completely, now sometimes that may mean you can't cancel. Right? If the top was x plus 4 and the bottom was x squared minus 6x plus 9, this is x plus 4 over x minus 3 squared. Well, what makes the bottom 0? X equals 3. So now you want to cancel. But you can't cancel out anything. So when you plug in 3, the top is 7, the bottom is 0. You have a vertical asymptote at x equals 3. If after you cancel, and sometimes that means you can't even cancel, but after you cancel as far as you can, and you get this, then plug in the Posner trouble point. Is it removable or is it non-removable discontinuity? That is a vertical asymptote. Okay. So now we're going to talk about evaluating limits at infinity. Excuse me, infinite limits. What happens to x minus 2 over x minus 3 as x gets close to 3 but a little bit more? If it gets really close to 3, well, the top is going to get close to 1. 3 minus 2 is 1. And the bottom is going to be a little bit more than 0. Let's write 0 plus. Why a little bit more than 0? Because x is a little bit more than 3. X is 3.0000001. Take away 3, well that's 0.2, 3, 4, 5, 6, 7 zeros and a 1. Small. Okay, and you say, well, it's not that small. Fair enough. Fair enough. I'm going to make x even closer to 0, closer to 3, excuse me, by putting in more zeros. That is 3 point, many more zeros, a million zeros. Well, then you're going to get 0.00 a million times and then 1. If that's not small enough, well, get even closer to 3. Put in 2 million zeros. The more zeros you put in, the smaller it gets. This is approaching 0. But it won't ever be 0. Why? Because we all know one number to put in that box to get 0. And that number is 3. X will never equal 3. X is approaching 3 from above. It'll always be a little bit more than 3. It says that right there. So you're going to have 1, and you're dividing by a very, very small positive number. Well, 1 over a small positive number. You can do it one of two ways. You can think of the small number like this, or you can think of the small number like 1 over, a million or a trillion. In either case, do the division. Take your calculator or what have you. Do the division. See that you're getting large. And since the numerator is positive, and if you're a little bit more than 0, you're positive, our answer will be positive infinity. If the bottom's getting close to 0, but the top is not, you're getting close to infinity. Sometimes positive infinity, sometimes negative infinity. What if you have the limit as x goes from 5 from above, and you have negative 4x over x minus 5? Well, the top is getting close to negative 20. Negative 4 times very close to 5 is close to negative 20. And the bottom close to 0. But since x is a little bit more than 5, when you take away 5, you'll have something left over. What you need to remember is not 0 over 0. For these problems, it's either plus or minus infinity. So I have not 0 on top, I have 0 on the bottom. It's going to be one of those two answers. Which one? Well, the top number is clearly negative. It's negative 20. And the bottom number is more than 0. It's positive. Negative over positive is negative. You have the limit as x goes to 0 plus, let's say 1 plus 1 over x. Well, remember, limit commutes. It's the limit or distributes. The limit of 1 plus the limit of 1 over x. As x changes to 0, changes to any number, 1 couldn't care less. 1 does not change. It's 1. So this limit is 1 plus this limit. You have 1 on the top, you have 0 on the bottom. That's infinity. Since you have positive 1 on top, the numerator is positive. Since x is more than 0, then x will be positive. So you have 1 plus positive infinity, which is infinity. Please don't say infinity plus 1. Infinity. Okay, let's look at a couple of others. Suppose you have this problem. Say the limit as x goes to 1 plus, I don't know, x squared plus x plus 1 divided by x cubed minus 1. Well, the numerator, 1 squared is 1, 1 is 1, and 1 is 1. 1 plus 1 plus 1 is 3, positive 3. And the bottom, 1 cubed is 1, take away 1, get 0. So since the top is not 0 and the bottom is 0, I know it's going to be infinity. We need to decide what the sign is. Well, the numerator is clearly positive. Now, if x is more than 1 and you cube it, if you multiply numbers that are bigger than 1, whether it's a little bit more than 1 or a lot more than 1, you're going to get more than 1. I mean, multiply 1.0004 by itself. And you're going to get, I don't know, 1.00482216. You get more than 1. And then if you multiply it by that 1.004 number, you're going to get more than 1. So this is more than 1. You take away 1, it'll be positive. If you have more than $1 and you go and you spend $1, you have something left. So the overall sign is positive. Now, just for the record, what if this were negative? 1 minus, I meant to say, not negative. If you have less than 1, you have 0.9999. And you cube it, you'll get less than 1. And if this is less than 1, you have less than $1 in the bank, and somehow you convince the bank to let you take out $1, you'll be very close to 0, but you'll be negative. You'll owe them. You took out more than you had. And a positive over a negative is negative. So sometimes you get negative infinity. You need to go over the fact that when you have a constant and you divide it by a very, very, very small number, that fraction is going to infinity. You need to convince yourself of that. Let's try this last one. Suppose you have the limit as x goes to 0 of x squared minus 2x over, say x cubed. Well, if you directly substitute, you get 0 minus 0, which is 0 over 0. But that always means trouble. You can't have a limit being 0 over 0. You need to do something. And what I'm going to do is I'm going to kill off the 0 over 0. I'm going to factor out an x from the top. And, just remember that x cubed means this. So you can kill off one x from the top and one from the bottom. If you wanted to have x cubed on the bottom and not x times x times x, well, that's also correct. Give me one moment, please. I killed off an x on the top, an x factor on the top, and I have 3 x factors on the bottom, and when I kill off one, I have 2. So, right now, what we have is the limit as x goes to 0 from below. I changed it to below, and we have x minus 2 over x squared. Well, the numerator is 0 minus 2, well, that's negative 2, a non-zero number. And any number close to 0, when you square it, it'll be close to 0, but positive. You square a number less than 0. You square a negative number to get a positive. So since we have not 0 on top and 0 on the bottom, it's infinity. And since the numerator is negative and the denominator is positive, we get negative infinity. Okay. That completes the lecture on infinite limits. Again, it was infinite limits, but our answers kept being infinity. Positive infinity or negative infinity. Okay, good luck with this stuff. Thank you.